All right, so today we're going to talk about Chapter 10 here, which is dictionaries. That's where we are. So I'm in Colab, ready to run this thing live. So I run their preliminary script here to get it going. All right, so now you can have a list. We've already talked about lists, which are extremely common and very powerful. I use them all the time in Python. Probably lists are the number one thing I use, and after that is probably dictionaries. They're both quite useful. So a list is just a series of elements in square brackets that can be text like this, or they can be numbers and so on. And then you can refer to it as an index. You have element 0, element 1. So lists of 1 should be 1, okay? If you want to go in the other direction and look up a word to get the corresponding integer, then you can't do that with a list. You have to have an integer for the index. But if you wanted to have, that's why they call it a dictionary. If you wanted to have, say, English words connected to Spanish words or something, then you wouldn't necessarily have an integer on either side of that. So what you can do, use curly braces instead of square braces, and then you have a dictionary. Now, there are no elements in a dictionary yet, but this creates a dictionary object. So now what you do, you can use any kind of data you want as the key. It's a key value pair. So I can set numbers element 0 to 0, and now when I print it, I have 0:0. So it's key value pair. You have a key, which can be any kind of data item, and then a colon, and then its value. So now I can set numbers 1 equals 1, numbers 2 equals 2, and now I have a dictionary where the alphabetical description of a number is connected to the integer description of the same number. All right, so to look it up, you use the key. You use the square brackets, and then in here, instead of putting an integer, like you would for a list, you can put in the key value, whatever it is. In this case, the key is strings. And all right, and we only have to put in 0, 1, and 2, so if you try to use 3, you get a key error. There is no element number 3. You can use the length, and that tells you the number of key value pairs. There's 3 such pairs in there, all right? All right, so it's a mapping from keys to values. That's what it is. And so you can have your state diagram. They really like these things. I'm not sure they tell me much, but there you are. 0 connects to 1, 1 connects to 1, 2 connects to 2, and so on. All right. So to create a dictionary, you could just do this. The way you make a list, you can use curly braces, and then you can put in key value pairs. Now notice that if you try to put in something that's not a pair, like you put in frog alone here, then it's going to complain. You can't do that. You have to have a colon and a value. You are not allowed to have just a value the way you would in a list. You can only have colon and then a value pair. Now it'll be okay. All right. I'm going to get rid of that in case it matters, because that's not in the original one. Let's get it back to the way they made it. All right. So now you can have a dictionary with nothing. That'll be an empty dictionary. All right. And you can make a copy of a dictionary with numbers, with dict of numbers. I see. So numbers is already a dictionary, and you can make dict again of it. That's interesting. I would have thought it would be numbers.copy, but you just make a dictionary of a dictionary. All right. All right. Now you can use the in element just like you did in list. You can find out if 1 is in numbers. That'll tell you if a key is in there. Now, the value 1 is in numbers, but it won't let you search for that. You can only search by the key. And if you've done database management like I have, you'd understand this. The key is a special place. By the way, another thing, I believe the key must be unique. So if I try to add another item here, that's 0, going to 4, I think it's going to complain. No. Well, that's interesting. I expected it to complain. Let's see what numbers looks like now. See what happened is this assigned 0 to 0. This reassigned 0 to 4. That's a little bit nasty that it didn't give me an error message. There's still only one value for 0, and it's the last value that was assigned here. Boy, I guess you can probably do it again then. To fish. I don't think the data type of the next one has to be a colon, though. I guess I can do this. And now 0 is now fish. So that's interesting. I didn't know you could do that. And that's a little bit confusing behavior. Okay, I'm going to put it back to the way it was. Okay, all right. All right, so that's in. All right, we talked about that. To see whether something appears as a value, you can use values. So number.values will create a sequence of values, and I imagine it's a list. So I can see is 1 in there. That's true. Now let's take a look at what number.values is. I'd like to know if I print this, number.values, and then I print the type of it. I think it's probably a list, but let's find out. Print type of number values. All right, I might have the right number of parentheses. We'll see. Yeah, it's a special class called dict values. That's interesting. Looks like a list, but there's a special class just for these values things. Okay. All right, so they're stored in a hash table. So in the hash table lets the in operator take the same amount of time no matter how many items in a dictionary, and this is related to a thing called Bloom filters, which are extremely wonderful. They can look up things very, very fast. All right, anyway, so you can write very efficient code doing this. So here, we're going to download a whole file called words.txt, and we're going to read it and split it into words, and we're going to see we have 113,000 words here. So it's a whole dictionary of a whole lot of words. All right. And so here's reverse word from previous chapter. This will reverse a word, and we're going to try and find words that are the reverse of another, stressed and desserts, where spelling one word backwards gives you another word. All right. So this is going to loop through. For every word, it's going to see if the reverse word is in the list and count it. So this is one way to do it. And they say this will take more than a minute to run because the in operator checks the whole list one word at a time, starting at the beginning. Now, to measure how long it is, you can use time, and that will tell you. All right. And the in operator is inside the loop. So I didn't see the time here. That's what troubles me. And they say it'll take more than a minute, but it doesn't look like they actually do it. All right, the total number compare, right. So the point is, for every single word, you have to look through the whole list to see if the reverse one is there. And so that means you have to go through 100,000 words squared. For each of the 100,000 words, you have to go through the list. So that's a ridiculous number of comparisons, like 13 billion. All right. All right, we can make this much faster with a dictionary. So this is going to create a dictionary that contains the words as keys, and the value is always just going to be 1. So that's a simple process. They could be anything. All we care about is dictionary. Now it's going to cause the key to be indexed with a hash table, which is very fast. And if you take 142, we go through it in great detail how hash tables get so fast. Anyway, actually 132. Anyway, so this is going to be much faster. Now, we're just going to see if the reversed word is in the dictionary, and the point is now each one of these comparisons is going to take a short amount of time. It does not depend on how long this is anymore. So now this one will be much faster, 10,000 times faster than the previous version. All right. Anyway, now I'm getting times. Now, why didn't we get times up here? I think they put an extra pound in. Let's get rid of that pound. That pound made it a comment. There, let's do this. There we go. Now it's going to be slow, and it's going to tell us something like a minute here. Okay. And this one's going to tell us that it did the whole job in 145 milliseconds. So, all right. A tenth of a second instead of a minute, so a whole lot faster. All right. So you're going to count each time a letter appears. You can again make a dictionary. And now as you loop through letters in the string, if you see the letter A for the first time, you can add it to the dictionary. And if you see it again, you increment the counter. All right. So this will be setting it to 1. This will be adding 1 to it. And I guess I can't execute code until this 1 minute one finishes. That's probably why they commented it out, saying you might not want to do it. But I'm willing to wait a minute to see it go. right, it's 621. I'll give it to 622 or 623. Now, the way a hash table works, by the way, is it turns the keys into a number with any of a variety of techniques, like just adding up the ASCII values and taking the modulus something, and then it uses that as the index for an array, so it jumps right to the location where it ought to be stored, and it's either there or it's not. And even if there are several elements with the same hash value, there's only a few elements there. That's why it's extremely fast. You do one conversion on the key to turn it into a number, then you jump right to where it would be stored. You don't go hunting through the list for it. It's therefore it takes constant time no matter how long the list is. It's very fast. All right, maybe I'm too tired of waiting for this. I'm going to stop it. All right. Anyway, now I should be able to run this stuff. All right, so I make a counter, then I set the counter of A equals to 1, and then I add to it, so now counter will have A containing 2. So this is going to count how many times each letter appears. So this is going to define the counter, and for letter in the string, it's going to add them. If it's not in the counter, it'll add it, and if it is, it'll add one to it. So this will give me a letter frequency, which, by the way, is something you very often want to do for cryptography. You can break substitution ciphers by getting a frequency chart. So that's the function, and here we're going to do the word Brontosaurus. And so there it is, Brontosaurus. Every letter is there, and you can see there's 2 R's and 2 O's and 2 S's and 2 U's. All right. All right, so now if you use a dictionary, it'll traverse the keys in a dictionary. So we're going to make a dictionary that counts the letters in banana. All right, that's value counts, which is the thing we defined up here. Okay, so that'll be BAN. All right. Now we're going to print the keys, which are the letters, BAN. Okay, to print the values, you can use the values. All right, and to print the keys and values, you could print them both like this. I guess that's one way to do it. You could also just print the dictionary itself, but there they are. All right, so we'll see this. All right, anyway, you can put a list in a dictionary. So here I have the key is 4, and the data, which can be of any type, is a whole list. So you can do that. All right. And you can't put a list as a key. The key has to be a hashable value, like a number or a string, and a list is not hashable. There is no way to boil it down to a simple number, at least no way that's supported by Python. So if you try to make a list of ABCD and then make a add it to the dictionary, it will complain. Unhashable type, like I say. It has to be able to boil this down to a number to get this speed up that comes through dictionaries, and it's not able to do that to a list. Although I must say I could think of ways to do it, but anyway, Python has chosen not to be able to hash lists. All right, and that's the game. The key has to be immutable. The hash value has to always be the same. All right. All right. All right, so many programming tasks, you're going to loop through a list or dictionary while building another. That's very common. So we're going to loop through the words in WordDic and make a list of palindromes, words that are spelled the same backwards and forwards. So here's is palindrome. This will check to see if a word is a palindrome. If the reversed word is equal to the word, return that. So now if we loop through the words, for each word, we can just see if it's a palindrome and count them. This should not take forever. It just needs to go examine each word once, and there's 100,000 words. It's not 100,000 squared, so this should not take forever. And it didn't. It only took a second or two, and it found that there were 91 palindromes. Okay. All right. Now we can make a list of palindromes. Here all we did was count them, but now we're going to do the same thing, and every time we find one, we're going to append it to a list of palindromes. So we're going to get the list of those 91 palindromes, and here's the first 10 of them. All right. That's pretty clear. Like I said, lists and dictionaries are extremely useful. Once you learn them, you use them all the time. And so if you only want the long palindromes, we're only going to get the ones with length greater than 7. And there's only a few of them. All right. C-memes. I don't know what that word is, but anyway. All right. All right. And there's a Fibonacci function. And remember, this is the one that calls, if it's get Fibonacci of n, it has to have Fibonacci of n minus 1 and n minus 2. So every single call decreases n by 1, but it doubles the number of copies in memory. So you end up with 2 to the n copies of this thing running in memory. So it uses a lot of memory and a lot of time. All right, so here's the call graph for that for n equals 4. They'll show you what it looks like. And there we go. Yep. So you have n equals 4. So now it has to solve 3 and 2. To solve 3, it has to do 2 and 1. And to solve 2, it has to do 1 and 0. So you have an exponentially increasing number of copies of it in memory as you go. And it's also extremely redundant. Here you are solving n of 2 and n of 2 again. Here's n of 1 resolved 3 times. You know, this is extremely foolish. All right. Very inefficient. So one solution is keep track of values that have already been computed. So you know 0 goes to 0 and Fibonacci of 1 is 1. And now every time you find a known one, you just use it, and you only add a new one if it's not already known. So if n is in the known, then just look it up and return it. This will make it fast. We won't have to do any calculations for repeated ones, and we'll only do this when we have to. That should be a lot better. And so Fibonacci 40 takes 30 seconds to run, but Fibonacci Memo takes 30 microseconds, 1,000,000 times faster. That's pretty cute. Let's give that one a try. 30 seconds is not asking too much. 2, 3, 4. It would be sort of nice to know the memory consumed too, but I'm not aware of an easy function to track that. 15. 20. Okay, 25 seconds it took, but the fast one is 22 microseconds, incredibly fast. Very nice. All right, so let's see, debugging large data sets. Yeah, if you're going to do something with a large data set, then test it with a small data set. Check summaries and types, like a total value and stuff. Self-checks and format the output. Yeah, these are all good plans. In the world of finance, you often do a large claim analysis. Find the ones with high dollar amounts and do those by hand to make sure they're coming out right. These are various debugging techniques. All right. Well, that's what I wanted to show you about dictionaries. I'm going to stop the recording.